Welcome back, guys and gals. We're at Chapter 4, Section 3. We're going to be looking at congruent triangles. Now, I need you to understand something. What we're doing with congruent triangles isn't the most important thing we'll do all year. However, it is certainly one of the more useful things that we will do this year in regards to helping us figure out other ideas. So think of congruent triangles not as an important subject on its own. It serves more as a stepping stone to help us get to other ideas that we'll need. So let's get started. First off, what it means to be congruent. If we have two items, so for example, say most people's hands are congruent. And congruence in the ancient world meant that you could take one item, so a hand, place a second item on top, and the two items would simply overlap, not at all. One would simply cover the other. No overlap, no gap, just one to the other. Now, if we have congruent triangles, there are certain things that we're going to have to abide by to prove or to show that two triangles do indeed meet this description. I mean, we can't go around all the time cutting this stuff out of paper and saying, do they match up? So, two polygons, not just triangles, but two polygons are said to be congruent if and only if their corresponding parts are congruent. So, for example, we've got a couple of triangles done up here. Notice that angle B, for example, has one arc, and angle J on this other triangle has one arc. That indicates that they're the same. Okay, they have the same measure. And remember, if things have the same measure, then they're congruent. If I look at A, for example, it has two arcs. Angle H has two arcs. And then finally, C and K both have three arcs each. That means that they are not only corresponding, meaning that they're in the same relative position. For example, my thumbs correspond, they're in the same relative position, but they are also congruent. So they are the same size, same measures. So not only do the angles have to match up, but corresponding sides also have to match up. So take a look. AB has one tick mark, and HJ has one tick mark, indicating that they are the same length. And we can go all the way around both triangles and see that they match up. So in order for them to be congruent, corresponding angles as well as corresponding sides have to match and be congruent. That allows us to write one of these. We call it a congruent statement. The congruent statement will show us all of these parts in a much more succinct way. So take a look. I've got triangle ABC is congruent to triangle HJK. And notice this was written very, very specifically. A matches with H if you're talking about angles. So A with H. B matches up with J. B with J. And then finally, C matches up with K. Again, C with K. So not only do I see that the corresponding angles appear in this, I can also find the corresponding sides. Take a look. I have AB occurring first and second, and that matches up with HJ occurring first and second. If I wanted to look, let's erase that. If I wanted to find, say, BC, notice that matches up with JK. So the congruent statement allows us to see not only the corresponding angles, but as well as the corresponding sides. There is more than one way to write a congruent statement. For example, for these two triangles, I could also talk about triangle BCA being congruent to triangle JKH. Notice B still matches up with J, C still matches up with K, and A still matches up with H. So this would also work as a valid congruent statement. This one would not. Notice that A and H appear first, and that's wonderful, but B appears second. However, what it corresponds to, in this case, J appears third, so not valid. So if you are going to write congruent statements for triangles, you must pay attention. Do you have the order correct? If not, you are telling us something that's, well, just not true. So let's see if we can summarize. Two triangles are congruent if and only if corresponding parts are congruent. Now this works not only forwards, but backwards as well. So the converse works. So in other words, if the parts are congruent, that means the triangles are congruent. If the triangles are congruent, again, the converse, then the parts are congruent. Now, instead of using all this wordiness, because notice two triangles are congruent if and only if the corresponding parts are congruent. Holy cow, that's ridiculous. Our book, and we are going to use this fun little acronym when talking about, congruent triangles. It is CPCTC. It kind of sounds like something out of the former Soviet Union. Here's what it means. It's short for corresponding parts of congruent triangles are congruent. We will use this as a reason in our proofs. So corresponding parts of congruent triangles are congruent. And again, we'll use that a little later on, but you definitely want to put a star beside that. You'd much rather write CPCTC and not, good grief, all of that. So moving onward, let's talk about the properties of congruence. We've talked about the properties of congruence when it comes to angles, when it comes to segments. The same properties of congruence also hold when we talk about triangles. So obviously a triangle is congruent to itself, so that's the reflexive property. The symmetric property also holds. So if I know that triangle ABC is congruent to EFG, then the reverse is also true, that triangle EFG is also congruent to triangle ABC. And then finally, the transitive property works as well. If my first triangle here is congruent to my second, and then my second triangle is congruent to a third, then that means the first and third are also congruent. So again, properties of congruence, they pretty much transcend everything. So we can talk about segments, we can talk about angles, we can talk about triangles, and still these properties hold. Right? Well, speaking of proof, let's talk about a fun little theorem. Okay? Take a look. You definitely want to put this on your proof cheat sheet. A lot of people forget about this theorem, and it is super helpful, particularly when we start working with triangles. Here's what it says. It's known as the third angle theorem. If two angles of one triangle are congruent to two angles of a second triangle, then the third angles are congruent. So in other words, if I knew C and B on one triangle, those angles, and I knew the corresponding angles, K and J on another, then this theorem tells me that A and L, even without me measuring, I have to know that they are indeed the same. Now, let me see if I've got this done up on a second slide. Nope, I don't. We'll have to do it here. So let's prove it real quick. We're going to do just a real rough proof here, nothing terribly formal. So we'll have our statements. We'll have our reasons. And let's prove this real quick. So our first statement is going to be, hey, we've got these triangles A, B, and C, and angles, C we said is congruent to, what was it, K, and angle B is congruent to angle J. And that'll be our given. Of course, we also would have the given that we've got the two triangles to begin with, but that seems kind of obvious. Cool. So our second statement. I'm going to say that the measure of angle C is equal to the measure of angle K, as well as the measure of angle B is equal to the measure of angle J, and that is by the definition of congruence. Okay, so we might as well make that transition. Third step, I'm going to say that the measure of angle A added to the measure of angle B added to the measure of angle C is equal to 180. The same is true for our other triangle. So the measure of angle L added to the measure of angle J added to the measure of angle K is 180. And I know this by the triangle sum theorem. So now that I have this, I could substitute one statement for another. So I could say that the measure of angle A added to the measure of angle B added to the measure of angle C is equal to, good Lord, the measure of angle L added to the measure of angle J added once again to the measure of angle K, and that is by substitution. Again, they both equal 180. That means they equal each other. One more round of substitution. I'm going to write it over here so I can give myself enough space. Goodness. The measure of angle A added to the measure of angle B added to the measure of angle C is equal to the measure of angle L added to the measure of angle B added to the measure of angle C. And again, We know we can take J and K out and put B and C in their places because up here in statement 2, we showed that they were equal. So there's the substitution step. Next, I'm going to do a subtraction and substitution step all in one go, just because I'm running very much out of space. So I can say 6, that the measure of angle A is equal to the measure of angle L. And my statement here is I'm going to say subtraction / substitution, just because I'm running out of space. Otherwise, I would show the subtraction on both sides. But again, due to space issues, I'm going to combine those steps. Last but not least, I can show 7 that angle A is indeed congruent to angle L. And we know that, of course, by the definition of congruence. So again, the third angle theorem. If I know 2 angles of 2 triangles that correspond are matching up, then that means the third angles have to by default. So again, very helpful theorem. Hold on to it. Definitely put it on your cheat sheet. Excuse me. And then last but not least, we've talked about this a little bit before, but let's get into some more details. One way we can talk about congruence with triangles is the idea of transformations. Now, we'll talk about transformations in a later unit in much greater detail, but let's talk about them a little bit today. So take a look. Triangle ABC is congruent to DEF, and notice, if we were to take this triangle and slide it, in other words, if it was out of paper, we could just move it across the table with our finger. We could move up or down, left or right, and slide it. The mathematical term is translate. Then notice, just because I move it left, right, or up or down doesn't mean that the triangle is different. So that means that ABC, this triangle, if it's congruent to DEF, well, then it's also congruent to what we call D prime, E prime, and F prime. So what that looks like, it looks like a D with a little dash beside it, and that's read D prime. This shows the new location of the triangle. So this is what we call a congruence transformation. Translating allows the 2 images, the original and the new one, to be the same. Notice the angles are the same measure, side lengths are the same measure, so they are congruent. We've got 2 other congruence transformations. Take a look. One is called a turn. In math, the technical term is rotation. So notice DEF is congruent to DEF prime. Again, our point of rotation would be here. So if I were to take that figure and rotate it, notice it stays the same size and shape. It's just its orientation has been off. And then last but not least, we call a flip. So if we were to take this, cut it out of a piece of paper and then flip it over, we get the mirror image. So because of that, we call it a reflection. Notice reflections give us the same on both sides. So E and E prime are the same, D and D prime are the same, and so on. So notice the corresponding parts of our congruent triangles are still congruent. So whether we translate, rotate, or reflect, we still end up with congruent situations. And the issue would be, can you identify so that D goes with this angle or F goes with this angle, and so on. So that's getting us into congruence. We'll get into more specifics in the next video, talking about, well, how else can we show that triangles are congruent without having to prove that all angles and all sides? Because as it turns out, we only need to know a little bit of information about our 2 triangles to know that, yes, indeed, they are congruent. If you have any questions, make sure you bring them to class. Have a good day, guys.